would have thought we'd still be here after 20 years. It's been a long, interesting journey. So my name is Dagdigian, and although I'm an owner and co-founder of BioTeam, I've worked really hard to demote myself in the org chart as we've grown, so I can stick to my real love, which is infrastructure and service of scientists. I really am a research IT infrastructure nerd at heart. I'm not cut out for management or actually running a company. And one of the great things about the last 20 years is BioTeam sort of allowed me to continue doing what I love. So it feels really amazing to be part of something that has endured for so long through so much rapid change and innovation. And we really wouldn't be here without all of our friends and clients and partners. So I do want to take the time to thank everybody who is, either listening to this live or listening to this in the future. I want to spend a little bit of time focusing and distilling some of the personal lessons that I've learned over the past few years about how to handle infrastructure thinking in such a sort of fast paced and constantly changing. So the current slide here is, I was trying to collect my thoughts, and I started looking back over my work to see, what I thought were the most disruptive or fundamental sea changes in life science research IT. The first four are on the slide that you're looking at right now. They're also likely very obvious to anyone of a certain age who might be seeing these slides. One of the sort of greatest honors was sort of starting out in this industry right out of school, early career. And I got to witness firsthand the sort of amazing lab side transition away from handwritten data stored in sort of version paper notebooks that were kept in filing cabinets and maybe scanned for a patent filing at some point in the future. But the other one, point number two, I think was really the fundamental sort of tipping point for me. It was the arrival of 64-bit operating systems that I feel unlocked bioinformatics, genomics, and computational biology. This was the operating system and hardware that allowed us to deal with big files, big data, and big memory. And I think the 64-bit OS coming at the same time that the Human Genome Project was exploding was kind of the perfect storm for us and allowed us to sort of make this really rapid transition. And then finally, I think the other thing is this last point, the research IT larger than the what it takes to run the entire organization. This was kind of the first major aha moment for me when I realized that the technology required to support a small group of really smart scientists commonly eclipsed what the entire organization was using to run the entire business. And the reason why this was such a big deal is that it allowed us to justify new products, do some new thinking and new technology, even if it was at odds with what the corporate IT standards were at the time. The most obvious example here was the rapid uptake of scale-out NAS storage in the research space, while enterprise was still sort of mainly dealing with direct attached storage and SAN attached storage. It really was the sort of research discovery world that drove that massive shift from SAN to NAS in our world. And really the primary driver was the overwhelming need to share data between multiple people, systems, and platforms. Next slide, please. So this is the second half of my transition list, a little bit less exciting here. I'm not going to read all of them here, but I think one of the other aha moments that happened later in my career was the abrupt rate at which the dominant file type of scientific data by size had totally changed on us. I used to concentrate a lot of my design energy on storing sequence data and genomes, but it really did feel like it was just a period of a couple of months or a very short period of time, when we started doing storage reporting and talking to scientists again, and we realized that, overwhelmingly image data and image-based data had eclipsed sequence and genome-based data, both in terms of rate of generation, but also how much space they were consuming on storage systems. The only reason I'm highlighting this here is because this is the type of stuff on the IT side we need to be thinking about and planning for. By the time you roll out your next generation storage landscape, are you really sure that images are going to be the dominant file type? I'm actually fairly sure they aren't. It's going to be really interesting to see what the sort of next major sea change is going to be. For me, if I had to guess, it's probably time series or video or something that we haven't even come up with yet. So if I transition sort of, going back through the major sort of transitions in my career, I wanted to distill it down to about 6 or 7 things that I've sort of learned over time. One of the things that I've learned is, for a control freak, this was the hardest philosophy for me to adopt. The scientific data that we ingest, store, and leverage has a lifespan that is going to be far longer than any sort of individual IT infrastructure or thing that we buy. So for me, my change of thinking was it just makes sense to sort of center my infrastructure thinking around storage, data management, and data movement. Everything else is just a transient, pluggable producer or consumer of my data that at some point is going to be replaced, retired, or refreshed. The second lesson here, and anybody who's seen my Trends from the Trenches talk is going to be bored at seeing this slide. This is already the most consistent truth in every sort of public, talk I've ever given in the last 20 years. The pace and rate of innovation on the lab side and in the science world greatly exceeds what we deal with on the IT and infra side. Our refresh and replacement cycles in IT are measured in years, while science and even instrument technology is moving much faster, in some cases month to month. So this is the sort of mental reset that you have to have if you're transitioning into supporting scientists. And this is the type of cadence that you have to think about, in particular, when you're building out multi-year plans. The third lesson here is, my job was a lot easier when I could build a data center or two and just demand that everyone and everything use resources that were housed in my walled garden. We have utterly and completely and probably permanently lost that battle on the IT side. The biggest driver is what I like to sort of refer to as sort of the pervasive diffusion of large-scale data producers and data consumers. These systems no longer sit at a data center. They no longer sit in a special building or even a special office or lab floor. They're now everywhere, inside and outside of our building. They're at the edge of our network. They're hiding under desks. They're on the lab side. They might even be in telco closets on a floor somewhere. So we need to sort of adjust our thinking and plan accordingly. The response to this lesson for me has been sort of a renewed focus on working with the enterprise networking folks and the WAN folks. You really do have to champion the need for sort of very fast circuits and very fast connectivity. And if you buy my argument that data producers and consumers have diffused everywhere, then you need to extend that thinking into your network planning, and sort of you need to diffuse those fast network circuits and fast connectivity throughout the organization. That means building the building, your perimeter, your connections to the internet, everything. A lot of my day-to-day consulting work is having these conversations with enterprise networking people who are sort of focused on the core, and they still think that only the core needs to have a fast network. So a lot of my sort of championing is, saying things like, no, you need to run 100 gigabit to each building. You need to have multiple 40 gig segments going to each floor. And oh, by the way, you need to be able to deliver 10 gig connectivity to a single laboratory instrument that has a fast network path, both to your central resources, but also out to the cloud. If there is anything that could be consolidated, it might turn out to be on sort of the network or sort of hub and spoke design of sort of how you connect things. If you think of data as having a gravitational pull, you're sort of thinking about bringing your workloads and your users into that data. This slide is kind of a long-winded way of saying that you could get some mileage out of consolidating connectivity. Not all of us have data centers anymore, but we still need a network hub. It probably makes sense for that network hub to not be exclusively cloud. For some people, this is physical real estate that they still own and operate. For others, this is when they sort of, make the decision that, okay, it makes sense to sort of put a stake in the ground at a well-connected co-location facility, either a rack, a cage, or a small suite, and sort of build out your connectivity in a well-connected environment run and owned by someone else. And then finally, if you really are sort of a startup or an emerging company, there are sort of some interesting product offerings that are starting to emerge now in sort of the zero trust or SD-WAN overlay space that can really provide sort of really interesting flexible overlay options for connecting your clouds, your people, your facilities, as well as all of the sort of transient relationships like partners and collaborators and CROs. The SD-WAN zero trust space is actually probably one of the more interesting, particularly when you talk about WAN overlays, is one of the more sort of interesting network segments right now in 2022. I talked a lot about storage. I could probably talk for hours about storage, but if I had to distill it down into kind of the core problems and sort of thinking around operations, this slide is full of obvious statements, but I think that the core ones for me is we still design and think about storage as if a human being pointing and clicking through a folder structure is the dominant use case. We still use file and folder paths to encode metadata that is very visually pleasing and obvious to the eye, project, instrument, lab, PI, experiment, but really doesn't make a lot of sense if your primary users are now machines or your primary access methods are programmatic rather than human beings sort of pointing and clicking. So that's kind of the big design thinking that we have to get away. We're well past the point where human beings are going to look at and browse all of the data that we're generating. It's long been easy to store very large amounts of data. Petascale storage hasn't been a hard problem in more than 10 years. It's still very much a grand challenge to manage, curate, govern, and move that data. So if there's one thing that you take away from this slide, it's that storing big data is a piece of cake. Managing big data is a fantastic and still yet to be solved problem. So a big part of this is, I think resetting expectations and resetting the social contract between IT and the scientists who consume that data. There's a cultural issue where I've consistently run into scientists who've built a career publishing around data-intensive life science, but they still don't really take an active hand in managing data. They still sort of dismissively talk about data and data management as an IT role. And those are the types of expectations that need to be reset. If you're doing storage, particularly planning for the petascale right now, you need to have scientists and scientific leadership directly involved in data movement, data management, and data lifecycle decisions. Those are all things that it's wildly inappropriate to have just IT be in charge of. And the earlier you can get the scientists to buy into this and to sort of adopt these methods, the better. And then finally, the most disruptive transformation of late has been, if you look at the requirements of machine learning and AI, where they typically need to always go back to the old data because they're retraining or reclassifying, that's kind of completely blown up a lot of our older sort of data storage, data tiering, and data archive methods. We're now at the point where effectively all in quotes of our data needs to be basically online or nearline in order to satisfy the requirements of the ML and AI people. Cloud decisions and operations. The only reason I put this, into the deck today is that even for organizations that are focused on co-located or premises-based operation, you still need a cloud presence or footprint, no matter how minimal. The primary driver there is eventually you'll have a capability need, an ingest aid, a data access need, or a collaboration requirement. That's just going to be flat out faster to put into the cloud. I'm still known for saying this, and I apologize for being a little bit blunt here, but spanning scientific computing workloads across multiple cloud providers is dumb, wasteful, and it's probably a sign of poor executive leadership. That will probably hold true until we get to the point where everything is in a container and everything runs under Kubernetes. And at that point, you probably will have workloads and environments that can span multiple clouds. For us, for BioTeam, we're sort of sober and practical when we think about using the cloud. And for me, I like to think in sort of hybrid cloud patterns. Consume the essential things from one, consume the essential things from another. And so the cliche example here is, we put a lot of life science workloads, we put a lot of research computing infrastructure into Amazon, but we still, for a lot of my customers, we still consume identity, authorization, access control, and SSO from Azure or Azure AD in particular. So that's the type of hybrid cloud pattern I like. Do my science in one cloud, but consume my identity and SSO resources from another cloud. That also fits how businesses tend to operate as well, which works out fairly good. And finally, I sort of really debated on struggling on whether or not to include this in my talk or not. The main reason that I added it is that it's absolutely at the top of my list if I was building a greenfield research computing ecosystem today. One of the hard lessons learned over the last, really over the last year or two is that you can no longer assume that it's an exclusive Intel and AMD x86 world anymore. You need to take active measures, and this is your InfoSec team, your operations team, your patching team, your end users. We need to ensure that our connected infrastructure and data ecosystems support ARM-based silicon, as well as the sort of traditional x86-based architectures. And this applies across the full stack. This is not just running multiple architectures in the cloud. This is making sure that your tooling, your libraries, your code, and your applications are all compiled separately or cross-compiled to take advantage of sort of the advancements, particularly in the ARM-based silicon ecosystem these days. So I'm going to leave this summary slide here for people who sort of stumble upon this deck or these slides at a later date. For those of you following along right now, this is definitely redundant information. So I'll wrap it up here and say with the next slide. So I really just want to thank everybody for their time and attention. I wanted to close out this slide with just sort of a collection of statements that, me and others have sort of made on stage, and really just sort of thank everybody for their time. And with that said, let's advance to and take some questions and discussion.